So now I'm going to be looking at problems that are related to conservation of angular momentum. And kind of like with conservation of linear momentum, pretty much angular momentum is always conserved unless, remember, how does angular momentum change? Well, angular momentum is I times omega. Either, in this case, either I can change or omega can change. But the only way omega can change is if really there's an outside torque. So in principle, in order to change, kind of like in linear momentum, the only way to change the linear momentum of an object is to have an outside force on it. The only way angular momentum can change is if there's an outside torque. So no outside torque means no change in momentum. So that's what we're always going to ask ourselves to decide whether or not angular momentum will apply. So playground merry-go-round has a mass of 120 kilograms and a radius 1.8 meters on r is equal to 1.8 meters, rotating about with an angular velocity of 0.5 revolutions per second. And let's just convert this into radians per second. It's 2 pi radians per 1 revolution, right? So the revolutions will cancel. I get radians per second. So 2 pi times 5.5 is just pi radians per second, okay? What is its angular velocity after a 22 kilogram child gets onto it by grabbing onto the outer edge? The child is initially at rest. So we're going to ignore the dynamics of like maybe there's some friction, maybe there's some torque that the child applies, and just simply talk about that he somehow gets on here without actually pulling on the thing naturally. So the child gets on it by hanging onto the outer edge, and he's now spinning around. Okay, so there's no outside torque on the system. It's a kind of collision. There's no outside torque. The child has no angular momentum to begin with. So the initial angular momentum is just I times omega naught. And we don't know I here, but we're going to have to assume something about it. We're going to say I, let's assume this is a disk. And so this is mr squared for I times omega naught. So this is 120 kilograms times 1.8 meters squared times omega naught, which is pi radians per second. Okay, and when I put that into my calculator, I get 120 times 1.8 squared times pi. I get 1221 kilograms meters squared per second. Okay, and so then I want to look at, well, what happens after the child hangs on? Is the I has changed, because not only do I have the I of this mr squared, I have to add in the mass of the child times r squared. The mass basically increased, so the I increased. And so this is going to be 120 kilograms times 1.8 squared plus the mass of the child, which is 22 kilograms, times 1.8 squared, and all of that times omega f is going to equal, by conservation of angular momentum, is going to equal this 1221. So I can solve for omega f by taking this 1221, dividing it by this value here. .65 radians per second. Okay. So it went from about pi, which is 3.14, to 2.65. 3 children are riding the edge of a merry-go-round that is 100 kilograms. Each has a 1.6 meter radius and is spinning at 20 RPM. The 3 children have these masses. If the child with a mass of 28 kilograms moves to the center of the merry-go-round, what is the new angular velocity in RPMs? Okay, so in this case, we have a child, like the big mass of this thing is 100 kilograms, and then I have an extra child here, here, and here, and each of these masses have 22, 28, and 33 kilogram. So if I wanted to calculate I, for example, I would just do the mr squared. Okay, we'll just assume this is like a disk. Actually, maybe I should use 1/2 mr squared technically, because you don't know. Basically, the total I is the I of everything together. So I'm gonna assume it's technically probably more like a disk. So I'm gonna say the disk, the I of the merry-go-round itself is 1/2 mr squared. And then I have to I have to sum up the MR squared for each child. This M is different for all of these, right? And so this is 1/2 times 100 kilogram times 1.6 squared. And we're assuming the children are sitting at the edge. Actually, I can just add up all these masses times the same R squared. So it's going to be 22 plus 28 plus 33, all times 1.6 squared. And this is about 340.5 kilogram meters squared. Okay, its initial angular velocity is 20 RPMs. That's revolutions per minute. And similarly, we got to convert this into radians per second. So 2 pi radians per 1 revolution. And in 1 minute, I have 60 seconds. So the minutes will cancel, the revolutions will cancel. Yeah, so 20 times 2 pi divided by 60. I mean, it's 2 pi over 3, but so 2.09 radians per second. Okay, so now I know the initial angular momentum. Now, when this child moves to the center, and he's over here, he no longer has the MR squared of his contribution is 0. So really, the I final, the rotational inertia is now a new mass distribution, the 1/2 MR squared, but really only two children now. So this could be 1/2 100 kilograms, 1.6 squared, plus now just 22 plus 33 times 1.6 squared. Uh, 268.8. Okay, and so because the omega f, like basically the final angular momentum equals the initial angular momentum, the angular velocity is just I naught omega naught over the final rotational inertia, moment of inertia. So that's 340.5 times 2.09 divided by 268.8. 10.3 radians per second. No, that can't be right. .65 radians per second. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.